was that ever a false alarm when I said that we were starting optimization? Okay, those other problems were just warm-ups to optimization, weren't they? Now we're finally starting optimization, okay? All right, number 1. Find the maximum or minimum values of the following quadratic functions and the corresponding values of x. Okay, we've kind of done that before, haven't we? It's basically the same as finding the vertex. They're just getting you used to the new way they're going to ask you to do that. So, to find the vertex, we could just use negative b over 2a, right? So x equals negative b over 2a. What is our negative b value? It's negative 2. So minus negative 2 is positive 2. And then the a value is 1. So our x value is 1. Okay? So the maximum or minimum values of the quadratic function, or this is the x value, and what is the y value that goes with it? It's equal to 1 squared minus 2 times 1, which is 1 minus 2, which is negative 1. Okay, so the vertex is 1, negative 1. That's basically what they're asking for in strange language. They asked you for the corresponding value of x, that's the x value, and they asked you for the maximum and minimum values of the quadratic function, which is the y value, so they're asking for the y value of the vertex also, okay? All right, so basically all these can be solved with negative b over 2a. Just be careful that trying to fool you, look what they did. They inverted the order so that it looked like the a value was 7. Don't be fooled, the a value is negative 1, right? And the b value is negative 2, and the c value is 7. Let's try it out. X equals negative b over 2a. So that's equal to positive 2 divided by negative 2, which is equal to negative 1. And the y value is equal to 7 minus 2 times negative 1, so plus 2, minus negative 1 squared, so minus 1, so that's equal to 9 minus 8, which is, or 9 minus 1, which is 8, okay? So the vertex here is negative 1 comma 8. What about this one? They're trying to fool you again by inverting the order. So the a value is negative 3, the b value is 2, and the c value is 3. So our x value is equal to b squared, which is 4. No, not b squared. What am I doing? Okay. And negative b over 2a, right? So negative b over 2 times a, which is equal to negative 2 divided by negative 6, which is equal to 1/3. And what is the y value? The y value is equal to, oh my god, this is going to be crazy. Negative 3 times 1/9 plus 2/3 plus 8. Yuck. Negative 1/3 plus 2/3 plus 8. So, 1/3 plus 8, which is equal to 25/3. Yuck. Okay. D. Y equals 2x squared plus x minus 1. So, it's in the right order. A is 2, B is 1, and C is negative 1. So we're looking for negative b over 2a, which is going to be negative 1 divided by 2 times 2, which is equal to negative 1/4. And the y value is going to be equal to 2x squared, so that's 1/16, plus negative 1/4 minus 1, which is equal to 1/8 minus 1/4, which is 2/8, minus 1, which is equal to negative 1/8 minus 1, which is equal to negative 9/8. Okay, so our vertex here is negative 1/4, comma, negative 9/8. What about this one? So it's A is 4, B is negative 1, and C is 5. So x equals negative b over 2a, which is equal to 1/8. That's x. Okay, so y is going to be a mess. y is going to be equal to 4 times 1 over 64 minus 1/8 plus 5. 4 divided by 64, that's equal to 1 over 16 minus 2 over 16 plus 5, which is equal to 5 minus 1/16, which is just whatever. 4/15/16, okay? I'm not in the mood to make that into a mixed number, although in math, normally we do that, right? 7x minus 2x squared. Okay, so in this one, x, or like the a value is -2, the b value is 7, and the c value is 0, okay? So x is equal to -b divided by 2 times -2, which is 7/4. So the y value is going to be probably kind of ugly. 7 times 7/4 minus 2 times 49/16. That's terrible. Okay. So that's going to be 49/4 minus 49/8, which is equal to 98/8 minus 49/8, which is equal to 49/8. So the y value happens to be 49/8. Okay. That was probably a little bit too much practice doing that, wasn't it? Okay. There wasn't really much difference between that and, like, the beginning of this problem set, except maybe those problems were a little bit harder, more fractions, right? It's good fraction practice for those of you who are rusty with fractions. All right, now we're finally going to do an optimization problem. A regular plot is enclosed by 200 meters of fencing. That means that if you measure all this fencing, the perimeter, it would be 200, okay? Has an area of A. Show that A equals 100x minus x squared, where x is the length of one of its sides. Okay, so they named this side x. They didn't say how many meters that side is, but this, of course, is x because it's the opposite side and it's a rectangle, and this side we don't know either. Okay? How about if we just call these unknown sides y? So we know that area equals x times y, right? Now, do we know something about y that we could figure out from x? Well, we do know that the perimeter is 200. We didn't use that yet. So if I add all the sides of the fence, and I could set it equal to 200 because the perimeter is 200, right? So 2x plus 2y equals 200, right? I want to get rid of this y because do you see how their expression has no y's in it? So I'm going to subtract 2x from both sides. I'm doing everything to eliminate the to put y by itself isolated on the left side. So I'm going to subtract 2x from both sides. I'm going to divide y by 2. And I get that. Y equals 100 minus x. Then I'm going to put that here. And now I have area equals x times 100 minus x. Then I can distribute the x, and then I get exactly what they had, right? Okay, so that was that. Now, these problems are challenging. And after you do a few of them, you're going to get the hang of it. But basically the procedure is this. They're going to have either area or volume or perimeter or surface area. Sometimes they have surface area. Okay? So basically you're going to write two equations according to these four possibilities. Once you write the two equations, you're going to have one equation which we'll call the optimization equation. That is the quantity you're trying to optimize. In this case, we are trying to optimize the area because we want to maximize the area, so we know that that's the optimization equation. The other equation we call the constraint equation because the whole purpose for that equation is to eliminate one of the variables from the optimization equation. As we said, since we're trying to maximize the area, this is the optimization equation. Okay, this is the one we're going to end up with at the end. the problem with the optimization equation, the reason why we can't just do everything from the very beginning, is because the optimization equation has two variables, and the only way we can optimize it is if we have one variable. How do we eliminate the y, the second variable? We take another equation, could be volume, could be perimeter, could be surface area. In this case, it's perimeter. And we write a second equation which has the same two variables, x and y, and then we solve for the variable we don't want, y, and then we get rid of y. Do you see? So, first thing you do, write two equations. Okay? Second thing you do, you figure out which is the optimization equation. Then you take the constraint equation, and then you solve for y. And then you substitute y into the optimization equation. And then you have optimization equation only with x in it, and then you find the vertex if it's a quadratic. Okay? Alright, so now we know that a is equal to 100x minus x squared. The area is maximized if the rectangle is a square. So if I adjust the x values, I can find a value of a which is as large as possible. And I'm going to show you that with the calculator because it's a lot easier to show a graph with the calculator. By the way you get a poly SMLT is second quit, okay? Okay, so I'm just going to put the equation here. What shape is this going to be? It's going to be a parabola. Is it going to be upside down or right side up? Well, it's negative x squared, so it's going to be upside down. If I graph it, sometimes I see nothing because these optimization problems, they have like values with like 100 and stuff in it, so it's like so high we can't see it. So now we are going to have to use appropriate dimensions. And the first thing we're going to have to do is we're going to have to make sure that our width is appropriate. In this case, the width is negative 10 to 10, which is how the grid always starts out. Do you see how the problem is talking about hundreds of meters of fencing? So actually negative 10 to 10 is not the right dimension, right? I might have, x might be as big as 200, right? So first thing I'm going to do is I'm going to change the x values. I know that x is not going to be negative, so I just put 0 as the smallest x value. And the largest possible x value is like 200, although it's not going to be that big. Otherwise, we just have a fence with the horses will be able to get out. So that's pretty good, except the fact that it doesn't look like a parabola. The reason why it doesn't look like a parabola is because this parabola is very high, because the amount of area is also hundreds and hundreds, right? Good thing about this calculator is we can adjust the x width by using window, but the height is a lot easier to adjust. We can do that by doing zoom. So we're going to do zoom fit, which makes the graph fit perfectly into our little rectangular screen. There we go. Oh, and there's our parabola. Okay? And now what we want to do is we want to know what the x value is right there in the middle when it makes the area as high as possible. We don't care about this negative part. That doesn't even make sense, right? It's like if we make the x value too big, then the area becomes negative. Okay? Alright, so let's do second calc maximum, which is 4. And then we're going to move the cursor so that it is on the left of the left of the thing. Oops. Toggle button lock. Unlock all buttons. Unlock all. I don't even know what that means. Okay. Moving it left by pressing left, 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 left. Okay, now I think I'm to the left of the vertex, so I hit enter. And now it's going to ask for the right bound. And then I'm going to go right, 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 until I am well to the right of the vertex. Make sure that you're to the right of the vertex before you stop. Okay, that's good. Enter. And then it asks me for a guess, which is any point is fine. And it turns out that the maximum, or the vertex, which is the maximum point, is x equals 50 y equals 2500. So the area is maximized if the rectangle is a square. Oh, we're supposed to show that. So we found out that the x value is 50. Do you see when the x value is 50? Y equals 100 minus 50, so that means y is also 50. So, oh yeah, it is a square. Okay? These optimization problems get pretty predictable after a while. Alright? So, we are done with our first real optimization problem.